This is video 3 of topic 5 on infiltration. In this video, we'll talk about a particular infiltration model called the Green and Ampt model. Infiltration is modeled as an unsaturated flow, which means that within a soil column, we have both water and air present in addition to the mineral grains. The forces that are present include suction or pressure, gravity, and friction. And in these models, soil usually starts as unsaturated, and then it fills as the rainfall progresses. The Green and Ampt infiltration model from 1911 represents the relationship between moisture content and soil depth as a sharp wetting front that separates the saturated soil at the top of the soil column from the initial moisture content at the base of the column. To show that diagrammatically, we have here the initial soil column. So this is our soil column here. This is the wetting front, which is assumed to be sharp, a flat line. This is the saturated soil, and this is the unsaturated soil below it. As a storm progresses, that wetting front moves deeper because the soil absorbs more and more water. So here you can see initially, and here much later on, that wetting front has moved down, and this is all saturated soil. The Green and Ampt model has 5 key assumptions. First of all, we assume that the soil under consideration is homogeneous and stable. What this means in practice is that we assume there are no significant flow pathways, no macropores. We also assume that the supply of ponded water at the surface is unlimited, so water is available to saturate the soil deeper down. We assume that there's a distinct, precisely definable wetting front. You can see it in this field photograph here. This is what the wetting front actually looks like. It's not perfectly flat, but you can see that actually it is clear. Okay, so we assume that that distinct, precisely definable wetting front exists, and that it advances at the same rate with depth. So this front will just move downwards uniformly. We also assume that there's capillary suction, or the pressure head below the wetting front is uniform, and it's constant in time during the infiltration event. Finally, we assume that the soil is uniformly saturated above the wetting front, and that the volumetric water contents remain constant both above and below the advancing wetting front. The volume of infiltration down to the wetting front is given as capital F. So this is one of the key variables in the Green and Ampt model, and it can be calculated as F is equal to theta S minus theta I times L, and that theta S minus theta I is called the moisture deficit, MD. Theta I and theta S are the initial and the saturated water contents, and L is the depth of the wetting front. We are talking about this as a volume, which is odd because I only have a unit of length here, right? This is millimeters or centimeters, and so it's important to consider that actually this is a volume. The volume of infiltration is the amount of new water that's added to the soil. We have this delta theta times the depth, but implied in there as well is a unit surface area of the soil column. So that area times the depth gives us volume. We then use Darcy's law, and this will be covered in more detail in topic 10. You may remember this from previous courses as the Darcy velocity Q is equal to negative the unsaturated hydraulic conductivity, which is a function of the soil wetness, multiplied by the change in head with respect to depth below the surface. This is going to be the equation that we modify to get to our Green and Ampt model. If we apply Darcy's law to the saturated zone and we simplify it, we get Q, which is the Darcy velocity, is equal to negative the infiltration rate. Okay, so this is a speed as well. It's negative because we're measuring it downwards, where Z is positive upwards. Okay, Ks is our saturated hydraulic conductivity, Ks, and it's used to represent conditions in the saturated zone, in other words, above the wetting front. Then here we have the change in head, the head at the surface minus the head at the wetting front, over the change in depth, which is the elevation or the height at the surface, minus the height lower down at the wetting front. If we start with this equation, and then we make some substitutions, we get to a useful result. So our substitutions are going to be the distance to the wetting front, where z is positive in the normal upwards direction, is downwards, so negative L. This means that the head at the wetting front is z plus psi, or negative L plus psi, and the head at the surface is, of course, 0. So we make these substitutions, this becomes 0, we put in negative L plus psi for the HWF, we put in 0 for the surface level, and we put in negative L for the distance to the wetting front. Then we simplify, and we end up with F is equal to Ks times 1 minus psi over L. This is the first stage, but I want to relate my infiltration rate to my cumulative infiltration volume, which is capital F. So that'll be my next step. Recalling that F is equal to L times theta S minus theta I, or L times the moisture deficit, we can rearrange, so we'll substitute into the last equation on the previous page, and this is the nature of the substitution. I just replace my L on the bottom with F over md, and then I have F and capital F, which is the relationship that I want. Now, this is kind of an odd-looking equation, and so you'll be wondering, how do we interpret this equation? The first thing is that the Green and Ampt equation represents the relationship between the infiltration rate, so how quickly rain can infiltrate into a soil, and the cumulative depth of the water infiltrated. And what you can see from this equation is that F decreases as capital F increases. We'll come back to that. Since the pressure head psi is negative, the infiltration rate, lowercase f, is greater than the saturated hydraulic conductivity. So we have 1 minus a negative, so 1 plus something. This situation continues as long as there's sufficient water at the surface for infiltration to occur. And what we mean here is that we have puddles at the surface that provide water for infiltration. The infiltration rate, as I mentioned earlier, then decreases as the cumulative infiltration, F, increases. In other words, F is a function of capital F, and greater values of capital F mean lower values of lowercase f. This is a very important point. To solve this equation, we need to estimate 3 different parameters. We need values for Ks, we need a value for Md, and we need a value for psi. Ks, it turns out, is pretty easy to find, and it's actually ultimately the limiting downward rate of water transmission as f approaches infinity. Md depends on something called the effective porosity and the initial saturation. Effective porosity is the space available for water flow. It's a little bit less than the porosity that we've been talking about until now. And you'll see 2 terms used. You'll sometimes see theta E, sometimes you'll see phi E. Note that both of them, however, are less than the actual porosity, and that's because some of the water will remain stuck to the grains in the soil. Finally, psi is the difference between atmospheric or gauge pressure and hydrostatic pressures. How do we use the model then? In other words, what happens when it rains? Do we get infiltration, or do we get runoff, or do we possibly get both? It's important to note first that infiltration is governed by one of 2 things. It's either governed by the rainfall intensity, I, of the storm, or it's governed by the Green and Ampt equation. If the rainfall intensity I is less than the potential infiltration rate, then F is equal to I. In other words, whatever falls as rain infiltrates into the soil. There are three rainfall scenarios possible. The first is that I, the rainfall rate, is less than the hydraulic conductivity. In other words, the rainfall intensity is less than the maximum downward hydraulic conductivity. Here, runoff will not occur, and this is because all of the rainfall infiltrates regardless of the rainfall duration. In other words, a light rain. If I is greater than F, then the rainfall intensity is greater than any infiltration rate that we could possibly have, and so runoff is very likely to occur because the soil simply can't keep up with the rainfall rate. This is our complicated case. And so here, the rainfall intensity is greater than the saturated hydraulic conductivity, but less than the infiltration rate. And so the time to ponding, so as that infiltration rate decreases, we're more likely to get puddles. And that time to ponding will vary for different rainfall intensities. So what you should remember from this is these three cases. This one corresponds to light rainfall, this one to heavy rainfall, and this is our complicated case. The Green and Ampt equation can also be used to determine cumulative infiltration, capital F, as a function of lowercase f. So here I'm just switching things around. One application is that we derive the volume of infiltration, Fs, that's occurring at the moment of surface saturation, where F is equal to I. So our infiltration rate is equal to the rainfall intensity. And again, here I've just switched the equation around and I've replaced F with I. Here I is greater than Ks, and recall that our capillary suction psi is negative. This means that Fs is a negative over a negative value, which gives me a positive value, which is what I would expect. Remember that the Green and Ampt equation predicts three possible cases, which are based on various rainfall intensities. So case A is where the rainfall intensity is less than the saturated hydraulic conductivity, and so my infiltration rate is just equal to the rainfall intensity. That's down here in A. Okay, and note that this is showing the saturated hydraulic conductivity, Ks. If I is greater than Ks, then F will be equal to I until we get ponding. When F is equal to its ponded value here, that's this corner point here. And then following that surface saturation, that's for lines C and D, we know that F decreases as the cumulative infiltration volume increases, and so as we get more and more rainfall, we expect that infiltration rate to decrease. All right, so this is our case where we have soil that's saturated from the very beginning. That's case D. Here we have the rainfall rate is equal to the infiltration, so whatever falls gets soaked up. Once we've reached a certain point where the soil can no longer keep up with the rainfall rate, we end up with a decreasing infiltration rate. And then this is the case where we have a very light rainfall, and so everything gets soaked up. Now, a major advantage of the Green and Ampt model is that the parameters Ks, psi, and the moisture deficit, Md, can be determined from physical measurements of soil. There are lots of data that are available on tension and moisture content, so we can just look those up. And in practice then, the Green and Ampt parameters are typically calibrated, especially where the equation is used in simulation models. So we would test our soil first, decide which of these parameter values give us results that match our field data, and then simulate from there. Here are some sample values tabulated below for a variety of soils that we would encounter normally. We have sand, loamy sand, sandy loam, and so on. The effective porosity, remember, accounts for trapped air and residual water. A more reasonable value to use in the computations is the effective porosity. So note here that there's a number of different symbols that can be used. Here porosity is tabulated as eta, but we've seen it before as phi. The effective porosity can be either theta E or phi E. I'm not sure why this is done, it's just confusing, but you'll see different symbols used. And then we have the wetting front suction head and the hydraulic conductivity and so on. Here's a larger version of that same table. What you should note is that moving downwards here, we have finer and finer particles from sand down to clay. And what you'll see is the porosity is not really predictable. But the wetting front suction head, or psi values, increase as we move downwards. So you can see here the wetting front suction head for sand is 4.95. Its typical range is between about 0.97 and 25. And as we get down to clay, for example, we're all the way up to 31.63 with a range of 6 to about 156, 157. The hydraulic conductivity decreases as we move from sand to clay. You've probably observed this in your own lives. If you see rainfall on sand, the rain disappears very quickly. If you see rainfall that's occurred over clay, there will be puddles on that clay surface for quite a long time. Of course, the Green and Ampt equation itself predicts the infiltration rate as a function of the cumulative infiltration F, not as a function of time. Okay, this is very important. However, since the infiltration rate is dF dt, we can convert the equation into a form that can be solved iteratively, so a trial and error sort of approach for F as a function of t. There are two useful equations that include this cumulative infiltration and time. The first point is that a determination of the time to saturation is also called the time to ponding. You'll see it as Ts or Tp, which uses the capital Fs or Fp equation given earlier to find Ts is equal to Fs over I. So here's one approach. There's another, though, developed by Zhou et al., 1988. This is an equation that connects the cumulative infiltration to ponding, Fs or Fp, to the time to ponding through this equation here. And we'll see some examples in the synchronous sessions on how to actually solve these equations. This is the end of video 3.